Greetings 2021ers, this is Professor Kaufman, and this video will give you an overview of how to get started on Project 1. It's meant to complement the document that is present here and show some live demonstrations and tips on how to get going, as well as complement some of the tutorial sessions that TAs will be putting on in this first week of classes. First, have a look at the document, which you'll find linked off of the course schedule. It's up, you can see the URL up here under our 2021, that's just P1 or P1.html. The first thing that many of you will want to do is to download the code pack that's associated with the project. We'll do that in just a minute. And this video will be linked up at the top of the assignment shown here. There's a brief preamble about what you're going to be on about. The general idea, though, is to do some actual C applications programming. Anytime that you would program in C, you have to be a little bit closer to the machine architecture that you're dealing with. And a good way to get an introduction to all of that is just to code some things that are, I wouldn't say mundane, but similar to what you've likely done in the past. So the first two problems mentioned over here implement a small plotting program that will create bar charts of stock prices based on the prices that are listed in a file, as well as then the third problem builds a small hash table implementation that has some amount of interactivity associated with it. Along the way, you'll need to make use of various facilities that are in C and are reflective of other things you'll likely have programmed. The stuff like reading data from text files, printing things in a certain formatted fashion on the screen, using some interaction with the user by reading some command from them and running appropriate functions, and then as well get into some of the weeds that C provides. For instance, the structs that it provides to lay out new data types. There'll be a stock struct and various hash table structs. And then dynamic memory allocation associated with malloc and free required in both of these. Generally, the grading for projects is divided along two lines. First, the one that's probably more important to all of you is that there's some automated testing. Just as you can type make test in labs to determine if your credit is full or not, so too in the projects there'll be a battery of automated tests associated with each problem that can give you some sense of how far along you are. And the other half of the grading criteria divides along the manual inspection criteria, where a grader will have a look at the code that you've written, possibly other documentation associated with it, although that's not the case here, and then assign some score based on those style criteria. For each of the problems, you'll notice over here in the table of contents, there is a section on the grading criteria. And if I just click over there quickly, you can see for this first problem, about 15 points for the automated tests, and then 15 total points divided across several of the functions for manual inspection. And the criteria for manual inspection are listed along here. And generally, if there's an algorithm to be used, specific syntax to be, or techniques to be demonstrated in the function, those will be listed here. Absence of those elements will lead to no credit. A question folks often ask is, how do I get partial credit if I'm not passing tests? This manual inspection is where it's at. That if you just can't figure out what's going wrong with the code, still do make a submission. You may not get full credit up here in the 15, but if everything looks kosher, then the graders will assign credit accordingly. All right, a few other sort of preamble elements. All projects will have a manifest or sort of table of contents of the files that's provided, so that when we download the zip file that's mentioned up here, this p1 code.zip, there will be this set of files that's presented over here. They divide roughly into problems 1 and 2 files, problem 3 files, and then some testing related files. And I'll talk about some of those things in turn. One thing I want to draw your attention to right away is in the middle column over here. There are a lot of provided files, some data files, etc. But a few of these are marked in caps as edit, and this is where you'll spend most of your time editing this particular C file that's provided but incomplete for problems 1 and 2. And then for problem 3, these files need to be present to build the program, but we'll have to create it, and we'll look at a quick and dirty way of how to do so. Okay. As you would seek to do anything associated with the problem, you're encouraged to make use of the make file that's provided. This allows you to automate several things, like if you're working on problem 2 and want to put together a program associated with it, you should be able to say make prob 2. I think one of the TAs mentioned that some of the targets might be a little muffed right now, but I'll attend to that after the video is finished. Anytime you want to clean out all your files, type make clean, and by default, if you just type make, this will compile all of the programs associated with the project. If you ever forget, if you type make help, this will list out the available features that the make file provides. This includes things like testing, also creation of zip files that you'll ultimately submit to Gradescope. And as was the case in the labs, if you type make test something, then various tests will be run. For instance, test-prob1 should run all of the tests associated with problem 1, test 2 down here as well. If you type just make test, it will run all possible tests for all problems. So make sure to be using that liberally. Finally, there's one important thing that I'll reiterate on, and we may actually play around a little bit with you can run individual tests. So this is our 15 tests associated with problem 3, 15 associated with problem 2, etc. If you're specifically trying to debug, for instance, this test number 6, use the syntax over here, make test prob 2, and then select test num equals 5 or 6 or 13, whichever specific test you're running. That will avoid running a bunch that you've already passed and enable to more quickly sort of get a cycle of, I tried something, let's see if that passes the test. We'll come back around to that later. Okay, as for a preview of the problems, the first problem has you plotting some stock data. It's relatively straightforward, where at the end of the problem, or problems 1 and 2, you'll have created this stock main program with supporting functions in the stockfuncs.c, and will allow you on the command line to say, I want to plot things that are a maximum of 10 wide, and I want to plot the data that's in this stock ascending.txt file. The program will call a series of functions that will open up that file, read all the data in it into various data structures in C, and then proceed to analyze it to determine a few things like where the minimum and maximum minimum and maximum prices for the stock are, and then create this little plot over here along with what the prices are. You can see several examples of that as we work around in these data files that are in the data subdirectory. They're all available to you and are probably part of the testing regime over here. So you can see in this case the stock started out high, reached a minimum here in the middle of the time frame, and then proceeded to increase. One interesting aspect that will be explored in this in the second problem is figuring out when the best time to buy and sell a stock is. If you've known anything about stock stuff, you'll recall that the best time to buy is when the price is low, and then later on sell it when the price is high, because this is money that's been created through perception of value. In this case, we wouldn't want to buy at the beginning because the price is too high, so we'll buy in the middle and sell at the end. You can see this aligns very nicely with the minimum and maximum prices for this stuff. On the other hand, there are some cases where that's not possible, and that's because the minimum price for a stock occurs after the maximum price in this particular range. And so you'll have to implement a small algorithm that is designed to figure out what the best sort of buy and sell point is. Oftentimes selling at the max is common, but you may have to buy before that, because the last time I checked, you can't go backwards in time to buy late and sell early at a higher price. So there's a section associated with that listed down over here, and as you'd be working on that associated with problem 2, then you might read a section over here which has some pseudocode in it, along with some implementation tips. And in addition, there's an optional makeup portion that says you can actually do better than this doubly nested loop over here, which has sort of a worse time complexity than is strictly necessary. So you'll want to be aware of that as well, that scattered throughout this, there are lots of implementation notes about specific functions. For instance, you may have a look first at the outline of functions. We'll have a look at that in source code form in just a minute. A few other notes on things. But then as you would get to actually implementing things, there's some tips and advice in here. That has to do with C syntax, with allocation memory, and about printing specifics. All these things are details that are pertinent to the problem that you're working on and are worth your consideration. Let's actually get started on this quick, because I think it'd be a good idea to see some of this stuff in action. I'm going to come back up to the top. Now, depending on what programming environment you're making use of, you may just want to click on this thing and download the zip that's associated with it. In my case, I want to get it exactly to where a particular terminal location is at. So I'm going to copy the link address over here, zip over here to my IDE. You can see I have the lab 2 code in this Seaside 2021 directory, and make use of that just a little bit later. Over here, I've got a terminal that's lined up in the same directory. I'm going to make use of the handy utility wget, paste that link in. Wget is short for webget, and it will download from online some file into the directory where the terminal is located. If I do an ls over here, you can see now I've got a p1 code.zip, and if I refresh my directory listing, there's that p1 code.zip. I can unzip here, that p1 code.zip. You can see it extracted a whole bunch of files into this, and if I refresh my directory one more time, you can see this P1 code directory is now created. I'll change in there and see a bunch of stuff in here. It'll also be a good chance for me to test whether that message that TA sent is correct, and I'll come up with a fix for the make file and so forth. So one thing I might do straight out of the gate is just to try to build everything. I can do that by typing make. Let's see. Oh, I'm in the wrong directory now. I got to actually change into P1 code here. If I type make, then I'll get partially some of this stuff compiled. Then over here, this hash set main.c is not present. If you check back over here, you'll see that's because I actually need to create that file, the hash funcs and hash set main. We'll do that in a little bit. For now, we actually built the stock funcs and stock main over here, and that's because to get you started, these are specifically oriented to be able to be compilable straight out of the gate. And so let's just have a look quickly at first this stock funcs.c. You can see over here that there's a description of what this function is supposed to do. Now let's make this full screen so we're not clipped there. However, there's very little going on in the body of the function. Instead, the instruction here is it's my job to write these functions, as well for stock free, and so on down the line, stock prints, stock seg, min max, etc. That doesn't mean I can't run the tests. So for instance, I could make test prob1 here. And this little testing script will be happily tell me that I'm failing just about everything in here. And that's not unexpected. I mean, the functions are not doing anything yet, so why would they pass tests? So just quickly, though, it's a good idea to look and remind, if you haven't picked up this in lab yet, there's a new directory called test results that has been created over here. And this is actually referenced in the test results over here. If I can just flip these two around quick, you can see each of the failures mentions there's now a file in test results, and then there's a problem1 test number 7 results.tmp, short for temporary file. And this lists what went wrong in the test. You can open this up in your text browser, or sort of IDE, etc. They're just normal text files. And if I open this up over here, I have slightly nicer formatting because this is actually a known format for Emacs, but no matter here. And you'll see a number of items up here which are worth your consideration. For instance, the failure messages up top indicate what has gone wrong. There are 2 failure messages. One of them is that the output mismatched what was expected. And I also got a segmentation fault. This is a memory problem. A few other items up here. Sometimes there's comments up here, but oftentimes there'll be a testing program that has comments in it about what the test is specifically supposed to do. So if you come down a little further here, we'll want to keep an eye out for more information about the segmentation faults, but the output mismatch is always described in this side-by-side difference over here. So I'm going to align that to the top of the screen over here. you can see, perhaps vaguely at least, that the output up to this point matched, but then I start seeing these symbols in the middle, which means there's a discrepancy between what the actual outputs and the expected output are. In this case, I got a very brutal message segmentation fault, which is not expected over here, and then a bunch of missing stuff over here. Sometimes this seg fault message shows up, other times it doesn't, and you need to look lower. The main point is something went wrong here and there's no more output, so how could I meet the expectations of this test over here? A little further down, you'll find some additional information. There's some line differences mentioned here, which can make it easier to identify if there's a single character difference between the expected and the actual stuff. We might see some examples of that later. But then finally, down below is a Valgrind log. Valgrind is a tool that we'll talk about this week in lecture that allows you to more quickly diagnose memory problems. And in all cases, as you have a memory problem, Valgrind reports more information about it. For instance, down here, there's a mention of an invalid read of size 8. Invalid reads are an attempt to go to some memory address and access the data that is there. But it's a seg fault in that the program is attempting to access memory that hasn't been granted to it by the operating system. In this case, there's a specific line number given that's in the testing program that's been provided to you that this is happening. Line 38, we'll go look at that in a second. And in particular, it's attempting to access what's at address 0. This address 0 is something you'll see often and is associated with null pointers in C. Their usual representation is all zeros, no ones about it, which translates roughly to decimal address 0 or hexadecimal address 0. And this is always out of bounds in C programs. When you assign null to a pointer as its value, then it points nowhere, but technically has address 0 stored in it. Any attempt to access that, to either read something from there or put something then there through a dereference set, will result in a segmentation fault. So let's look quickly then at this test file. Now this is provided to you, but I trust my code much more than I trust the code that students tend to write. So in most cases, as you'd see a problem in the test file, it is not a problem with the test, it's a problem with something that your code has returned. Let's open that up here. To come back up and we can find this test stock funcs.c that's mentioned right here. And if I go to line 38, you'll see that the code above it is where my code in stock funcs is being called. So this stock new function that's supposed to return something. And then line 38, I'm attempting to access what is the data file associated with that, making use of the arrow syntax. This again implies that there is a pointer to a struct. That's what this stock thing is. And I'm attempting to access one of the fields there. On the other hand, this is saying that going to address 0 is no good, which makes me suspect that this stock that was returned from this function is in fact null. I'm going to check quick and have a look in my implementation file, that stock funcs.c that's up here. And indeed, when I look at stock new, all it does is return null. And to that end, the stuff that is printed over here then it requires to dereference that null pointer, which is always going to seg fault. So the first step along this lines would be to not return null. To do so, I'd probably need to allocate some memory for it. At this stage, then you might want to look a little bit at the documentation. For instance, it'll mention that the stuff that comprises stock should be heap allocated, making use of the malloc function. And it also mentions that this is a function that creates some memory and populates it with some initial values, and so should not make use of the free function. So let me eliminate this little write me, and I'll give myself a stock t pointer, stock, and I'll malloc some stuff. Now here's what you have to remember, a few things that we talked about in lecture. I need to allocate the correct amount of space associated with a stock. And for that, C provides this nice size of operator. We've seen it used for ints and so forth in lecture, but you can also use it on new struct types that are defined elsewhere. Incidentally, if you want to know what's in a stock, then you'd want to look at a header file. Over here is stock.h. You can see it here. And if you open that up, it gives you the recipe for what comprises a stock. Every stock comes equipped with the following fields, or local variable names. Although the technical name really is fields of the struct. There's a pointer to a data file. There's a count, that's an integer, a double array, which comprises the prices for the stock at various moments in time, and then an integer that says the index of the minimum and maximum and best buy and best sell points within this array over here. Now that is a bunch of fields. It's probably 4, 8, 12, 16, 24, 28, 36 bytes or so. And this size of spares me the need to count manually for this and is much safer as I change mine about. I'll probably allocate 36 bytes here that malloc will return. All I have to do at this point then is to return that. So I'll return stock instead. Let us then, as we've made some source code changes, see how we do on testing. Now if I type make test prob1 again, what I will find is that there will be a recompile of some things. So the first lines that come up here, it will detect, oh, there's been a change in the source files, and so the program will be recompiled before the tests are run to reflect those new changes. Handy features of makefiles at that. You can see that I am still failing all of these files. I'm told in VS Code you can actually control click on this thing to see the update over here, although some students will just keep it open. In my case, it's over here. And as I would look at what I hope is the updated version of it, I see, yeah, I've actually made some progress, and that segmentation fault over here is now missing. However, some of the things in here have to some extent incorrect values. So for instance, the stock count is 0. I apparently have the nils or null pointers correct, but all these things are supposed to be -1s instead of 0s. You can see down here some mention of that in the expected output here, it's all -1s, and the actual output, it has 0s. Further, if you look lower, Valgrind has some common complaints here, that there's some conditional jumps based on uninitialized stuff. Now this is a somewhat deep stack trace, but it starts out in, again, that test stock funcs at line 38. So let's look again at that. Over here, test stock funcs, and here, that's right. Here's my line 38 for that. And you see, this is again where I am printing out the data file associated with this thing. Importantly, while I malloced some memory associated with the stock and returned it, so it's now got a valid memory address and there's space for all of these fields, didn't bother in my code yet to go through and initialize any of those things. And malloc memory generally is uninitialized, so its values can't necessarily be trusted. To that end, the next steps in my function are to go through and initialize all of these fields to be some default value, so it has a well-defined value and hopefully matches what the expectation is. You can see over here it's mainly nulls and -1s for things to indicate that haven't been set properly yet. So for instance, if I come back over here and at the very least say, hey, this stock arrow data file, that's supposed to be, if I remember right, in the header file, a pointer, and it's initially null until this thing has been set elsewhere, so I'll set it to be null. If I save that and want to see what the effect is, I could rerun this and take up a lot of time, but really I'm only interested in this first test, so I'll make use of the test num equals 1 right now, which will only run this first one and actually print things on the screen for that. Let me make this a little wider, so I'll run this thing. You can see up here it's just running a single test, taking just a second, and then that output that was going on to the temp files, it's still there, but I have it directly in my terminal as well. And you can see I got the nil right here, and the nil right here. Maybe we'll need a -1 in a second. But I've also eliminated, this is now on to line 39 because the printing of the data file is no longer uninitialized. Valgrind is very good at detecting things that you forgot to initialize but then used later. This goes for malloc space as well as some stack space, local variables, that if you neglect to initialize that stuff, then Valgrind will gripe at you at various stages. So then I might move at this stage to say I also need to initialize something else. Here's the header file, the count. Let me set my stock count equal to -1. And here I can then rerun just this single test. I don't have to wait around for everything else. If I'm looking at the many conditional jumps or moves here, which are all the uninitialized stuff, I'm looking over here and I see I'm now down to line 40 in the testing file. And that's because, I got this count right, and we'll need to initialize prices later on. Then if I look at a wide version of this, you can see here the stock count is matching up nicely. So at the end of this little regime, I should end up having -1s on all these, and testing sort of should pass. They'll all be initialized, so these Valgrind errors will go away as well. And so these are not separate problems, the output mismatch and the Valgrind problems that are reported below. They are instead inimically tied together. Now, in some cases, you can get exactly the right output up here, in which case you won't get a side-by-side diff, and yet still you'll have some Valgrind problems over here. And to that end, be aware to look at for both of those things in here. I feel like we should just bang this one out. So let me get over here the different fields set up, and then my my stock funcs file over here, and I'll just get the rest of these here. So here's prices, that's a pointer, so I'll make it null, and then count should be min index, and here we can change this to max index. And then here's best buy and best sell, all initialized. Let's run this one more time and see how we do. And hey, 1 out of 1 passed. It's unlikely that the remaining tests will pass, but may as well have a look at it. I'll eliminate this test num equals 1, which means rerun all of the tests associated with problem 1, and indeed haven't quite done this stuff correctly yet. So the next step might be to look forward to the next function over here, which is to free stuff. And this is the counterpart to it. Now, this is a little bit more complicated because there will be some fields within the stock, like this data file and this prices, that may in turn be mallocked in addition. And so we'll need to check if these are non-null according to the documentation here, free those, and then free the stock. But that's part of the assignment, so I'll let you continue and grind on that yourself. Generally then, at least for this first problem or two, you can work sort of straight ahead by grinding through the various functions in here that include printing, setting the min and max once you have some arrays for it, setting the best buy and sell point, and then you'll advance on eventually to working with some of the files that are present. If you're curious what kinds of data these stock files comprise, they look sort of like this, where there's just some string describing a time. You can ignore that, and then a price at that time. Each of these entries then should be read into an array, and there are several examples in this data directory of various stocks. So for instance, here are 2 time points. Versus here's some actual stock data on Facebook, which has a slightly different time format, but we're not really interested in the time. Just ignore this part as you read it and have a look at the prices over here. If I remember right, this was a bad day for Facebook. When it's had many good days, but also some bad days. Additionally, there's stock data from Google and Tesla on some various dates there. So that, I think, more or less takes us through what I want to say about the first and second problem on Project 1. The next and final problem, the hash tables business, deserves a little bit more description as well. Importantly, you're going to be implementing a data structure here that I am assuming you've seen before. It is a hash table that makes use of separate chaining, and I'll say just a word about what that means in case you have learned it and forgotten. But if you've never seen hash tables before, I strongly encourage you to start doing some rigorous review, as my understanding is that they are covered in CSI 1913 or 1933, which are the UMM's prerequisites for this. If your particular data structure data structures class never introduced this, then there's some links and references here that you might use to ramp up. I want to jump down to my picture, the diagram of a hash set. So hash tables are great for backing up 2 variants of, or sort of conceptual ideas for data structures. Sets, which are collections of unique items, and maps, which map a key, which is also a set of unique keys to some value that's associated with those. We're opting for the set implementation here, and we have one minor variant that'll be important to discuss. Come back down here to the picture. So here's a picture of what the ultimate hash table is going to look like. And this divides nicely into several parts that I'll want to reference as we talk about the implementation. Up top, there will be a struct, which is called a hash set T. And it has several parts to it. There's a count, table size, and then several different pointers. The main feature of a hash table is a fixed size array down here. And this comprises the sort of table part of the hashing a bit. Each of the entries of this table, they point to someplace else in memory, which begins one or more items in a list of stuff. For example, there's no list attached to entry 0 here. Whereas if I come down to table entry 3, this points to a list that has 2 items in it. The defining characteristic of these items is that they each have a hash code computed for this element that's in it. For instance, here is Summer, and her hash code is 593. That element, if you take it modulo the table size right now, 5, will have a remainder of 3. So too will Rick. Whereas Beth, if I take this 967 modulo 5, then I'll get a remainder of 2, because it's 7 here. And the tiny Rick has a modulo of 1, because we divide by 10 and then divide by 5, and you get the 1 over here. So each of these elements here is grouped into a bucket of the hash table that corresponds to what their remainder for their hash code is. The hash code function is provided to you, so you can say what's the hash code of Jerry, what's the hash code of Shummer, and it'll spit back a number, oftentimes an enormous number that looks like these things, and allows you to then to properly place the hash elements into these. Now, since it's expected that as you add elements to the hash table, there will be more than one element that maps to the same hash code sort of entry over here. So for instance, Jerry and Morty both map to entry 4. The separate chaining technique allows for this collision to be resolved by putting them in a little linked list down here. So far, we've talked just about the black arrows over here, and this is a sort of standard hash set implementation. We add one twist to this, and that's as you add things into a hash table, all semblance of order sort of goes out the window. Want to add something else into the table, the hash it, if I find out it's is modulo 5, it equals 4, then I'd add it to the beginning of this list over here in front of Jerry. Lost is the fact that it's the most recently added item. And that long before it, there were other things that were added. So as we add in, there's also this blue set of arrows over here that comprises what was the order that things were added into the hash table. And so the very first thing that was added is pointed to by this order first. That's pointed down here at Rick. Following that was Morty, and you can see each of the little nodes over here has 2 different pointers. One that allows it to point to the next elements in the same hash bucket, and then one that points to the next in order that the hash elements were added. So after Rick comes Morty, after Morty comes Summer, etc., etc. One of the consequences of this layout for hash sets then is that as you are adding an element in, you'll need to add it both to the buckets that's associated with it, and also link it into this linked list of elements that represent the order that items were added in. For instance, if the next item being added hashed to this index 2 here, then you'd add it to the front of this little list, so it'll precede Beth over here and be pointed to directly from the bucket associated with 2. And as well, then, we'd have to find the last element of the current list. In this case, it's ported to by order last, as Tiny Rick, and link its order node, or sort of order pointer over here called order next, over to the new element that precedes Beth, and then redirect this order last to that new node over here. This allows you then to visit each of the elements in the hash table in order. So go from Rick to Morty, to Summer to Jerry, from Jerry to Beth to Tiny Rick, and then on to whatever new one is over here. And that's part of what one of the functionalities that the hash set provides, is to print out items in the order that they were added in. I'm noticing here, I think this should actually be element count or elem count, rather. I waffle a little bit between item and element in the hash table. And we can check quickly over in the code itself up here at this hash. Let's see, hash set.h. Indeed, it is elem count, so I'll adjust the picture mod to reflect that slight typo. So here are the two structs that comprise the hash table then. First, there's the hash set itself, and it has then a pointer to the table itself, along with these pointers to order first and last, and to element counts and so forth. And then, in addition, there is a node type that's specific called hash node, and it has space for a short character array or string, and then these two different pointers. What's the next thing in the table? So what's next to me in the bucket? Those would be the black pointers in the picture, and the blue pointers, the order next part. Don't be intimidated too much by this star over here. What this table is an array, and each element of the array is a pointer to one of the hash nodes that comprises that bucket. And so over here, as you look, you'd see this hash node field itself is a pointer, and it points to this sequence array over here, each of which has a node. The value in there could be null, as in there's nothing in this bucket, or it could be a pointer to a node over here, thus the sort of doubly indirected pointer. Now, just getting started on this is a little bit trickier than problem one, because as the manifest indicates up here, if I look at this download, you actually have to create this hash set funcs and hash set main over here. Hash set main is meant to reflect an interactive experience with the user. You can see some app demonstrations of that in the section over here, the demonstration. For instance, you can print out and see that there's an empty hash table over here, ask what is the structure of the hash table, and it'll print out various stats over here, including the fact that an empty hash table has all empty buckets. But then we can add some things, print it out, show the structure, etc. And over here you can see the structure here prints out the hash code associated with this thing, the key or the elements that store there, as well as what order-wise is the next thing, including a null over here. So some semi-complex printing within this structure function. And as we add more things, more stuff comes over here. So this application has two parts. The first is the sort of set of functions that allow you to manipulate the hash table, and then this main interactive function. Now, if that sounds vaguely familiar, it should, because this is exactly what you did in Lab 2 associated with a linked list application. And that's why over here in my sort of code setup, I've got Lab 2 handy. And what I'll do is just to copy over some of those linked list applications, as they are going to be handy for the stuff that's present for the hash table. So there's a list funcs and a list main.c over here. For reasons I'll explain in just a second, I'm really only going to copy over the list main part over here. And then I want to rename that. So move, that's the Unix command to move a file, but it's also for renaming list main to hash set main.c. And then I want to create a file that is called hashsetfuncs.c. Hashsetfuncs.c. New file there. And over here there is hashsetfuncs.c functions. There's a long listing of which functions are needed for this. So I'm going to copy this thing in over here down to this thing. There's there. And this first function, hash code, is provided. It's part of the project spec here. And you can see it right here. So I'm going to copy this stuff up top there. And the last thing I want to do then is going to get rid of this thing is to include the header file hash set.h so that I'm in agreement with the function in there. Now you can see none of these functions do anything yet. They're all stubs right now. That's not a big deal at the moment, and we can replace some of those as we start working on stuff. In addition to that, I'm going to have to make some changes here to that hash set main, which was actually my list main. First thing I might want to do is change this to the hash set.h here. Part of the reason I'm copying this is that you're required to do the same kind of command line echoing that is present in the linked list application in this hash set function to be compatible with all of the testing regime. So to that end, the echoing is built in here, and I've got reminders of how to do that stuff. And so the next thing I'd probably do is start making some changes here to the list t, because it should be a hash set t instead. All right, had to take a quick minute to change and clean up. Let us finish this out here. We had left off having a look here at how to adapt this list application main to our hash set setting. And we'll need to make some perfunctory changes in here. Obviously, we're not going to be dealing with lists. We'll be dealing with hash sets. So let me make a few changes commensurate with that over here. I got hash here, and this will be a hash init. I'll comment that out for now. We'll maybe call this hash instead. In addition to that, the prompt is a little bit different here. So we had list here for our lab application with lists. But if we pop over here to the hash set main demo, you can see it's instead this little HS arrow arrow. So I'll make a copy of that and plop it down here to get rid of that thing. And then as we continue looking around here, I've got an exit. It'll be called something other than insert. And so, but it'll probably be called something similar, and I'll want to maybe preserve some of this stuff. So I'm going to make use of an editor technique that is present in all text editors worth their salt, which is to create a block comment. I'm going to highlight this stuff here. And then usually there's a keystroke on VS Code. I think this is Control /, or on Apple it'll be the Command or Apple key /. My key is a little different, but it creates a comment out of everything that was there. Later on, if you decide, oh, I actually want to make this code live again, there's usually some inverse keystroke, like might be Control / again, or Control Shift / whatever it is in Emacs here, but makes the code live again. Extremely useful as you're working on stuff and you decide, oh, I don't want this to be here right now, but I don't want to get rid of it yet. We'll leave this stuff on over here and leave this list clear to be dealt with at a later stage. Let's see, I made a change up here. Instead of list.h, we got hash set.h. This is looking reasonable so far, so I'm going to come over here and I'll do a make prob3, which is going to try to build the different codes involved in problem 3, that hash set main.c and hash set functions. Let's see, an unused variable. Okay. So minor quip here. So this hash set here is a variable that's not used in any code anywhere else. And that's sort of my intent right now. Didn't want to mess with it. And GCC gets suspicious of those. Like, if you declare this variable, shouldn't you be using it? And if you're not using it, shouldn't you get rid of it? I don't want to get rid of it, so we'll get GCC in line by using it in one of these functions. If I save and compile now, I think this stage, there's an implicit declaration of this. Let's see, hash init. Let me just check my header file quick. Hash.h. Hash set init, I should say. There it is. Okay, that's cool. So I make prob3. and then too few arguments. Oh yeah, unlike the list version, you're supposed to pass in a second number, which is what is the size of the initial table that this hash is supposed to have. Now we could pass in a constant there that is just like 7 or 5, and 5 seems like the obvious one because that's what's used in the examples. But it's actually a symbolic constant, this hash set default table size that's pound defined to 5, that is specified to be used in these cases. I think if you search around here, hash set default size, use your clearing it with hashes, constant, blah, 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 etc. Paste this in here now. We'll later on talk about what this pound define is in contrast to global constants, but for now you can see it as a way to give certain constants names that have a little bit more human meaning than just the number 5. It's a good way to avoid the magic constants that are out there. Finally then, if I try one more time, let's see, some problems over here. Unknown type name hash set t hs. Okay. In my hash set funcs, I'll need to pound include hash set.h. That should fix up those things. And then finally, I have a late stage compilation error, which says this hash set main is using hash set init here. And over here in that C file, I don't actually have an implementation for it, just a stub. So let's add a plunky definition for that. It just is return. Now it's the only function that I have called in over here. And so these remainders can remain stubs over here because they're not actually used yet. But should, I think, then allow me to build. Yeah, okay, so I've got a build now for this thing, then I can run, it says hash set main, and it's there, and I could, type various things. They're all going to be unknown right now because they break down over there. And in fact, oh yeah, this linked list demo business, that doesn't look quite right either. I can at least exit according to this. But I can now run the tests. So I can do make test prob 3, which will compile and run some things. And of course, since I'm not doing anything right yet, I'll expect failures over here. So I'm going to open up this temp file and see what the dealio is. And you'll see the first thing it identifies is up here, it says linked list demo when hash set application. That's actually pretty easy to fix up. So if I come back over to the main, it'll be this stuff up here. And to spare you the pain of having to actually type all that stuff out, there's a section here in the spec that gives you, here's the printing to be done to print that little preamble set of instructions. So I'll plop that down here, re-indent, leave a little space up here. And then nix this thing. Importantly, one of the things that we've gained from copying this main over is, again, that echoing business. And we can check that in just a moment to make sure that all's well there. But the other thing that we probably want to do quickly is, because there'll be confusion otherwise, the command to be used to exit the program is quit. And right now, I think we have it as exit. So I'll put a quit here and a quit here. And we'll see if that gets us any better. So failed all tests. Let's at least try that, test num equal 1 to see if our printing sort of fixed things up. That didn't quite work yet. Print is an unknown command, but the rest of the stuff is looking good. So if I come back into main, find that, let's see, do I have a print someplace? Print. Ah, here it is, print. Okay. And so I can now make this part live, and I won't bother to do anything yet because I haven't implemented that hash set function, but at least, in the event I'm printing out something, printing out an empty thing, it'll be okay. So that's test code change, one more time. Hey, we got our first test pass there. It's possible that maybe the second one would pass as well, but that's probably sufficient now to get you an idea about where to go. The next steps then will be to progressively implement more of these high-level functionalities by opening up parts of main, and then in the hash set funcs, implementing additional support functions that are in here. Now, importantly, one difference from the first couple problems is that you cannot work on these functions necessarily straight linearly. That instead, to determine if the printing function actually works correctly, you'll need to have the, right elements maybe in ordered over here, but that requires you to actually have some elements in it, and so you also have to have the hash set add function implemented. So at least a couple different functions that will conspire together to create this high-level functionality. That's generally the case for data structures, that they are taken as their own unit. And if you're maintaining proper abstraction boundaries, you don't look inside the data structure manually by chasing pointers. You use accessor functions like printing or contains to query properties of it. That does make it a lot harder, though, because you have to get both functions right in order to implement the functionality correctly. But generally, that's the fine art of coding, is getting everything to cooperate together to manipulate one shared piece of data. And it's something that you'll get a lot of practice on in this problem. As you would wrap up your project, then you would probably want to turn your attention over here to the submission guidelines. And what you'll see over there then is that the first step is, I guess the step before this is to make sure that you're satisfied with your implementation. And you can do that by typing make test. This will run all of the tests, or problems 1, 2, and 3 on it. It's a good idea to do so one final time before submitting. I can press Control-C to cancel out of that, and generally Control-C is a good keyboard shortcut to know on terminals. It sends an interrupt signal, which usually stops a program from running and gives you your prompt back. Handy to get out of trouble there. But if I'm satisfied, then I take make zip. And this would, as in lab, create a zip file of all of that stuff. So as I look in this directory here, you'd see this now p1 code.zip shows up. And this is what I'll upload to Gradescope. And the instructions here then walk you through similar semantics to what's happening in the lab. I think in here it's called an assignment, but don't let that fool you. It's a project. And importantly, you'll want to make sure, that things upload correctly. If you try to upload too many files, Gradescope complains, but I think there's some warnings that'll be printed as you make a zip about that. As well as then wait around to see if the autograder produces results that you expect. Generally, it's your responsibility to verify that you uploaded the right thing, and that the tests that you expected to pass on Gradescope as well. Two things on that. There have been many students who precede you who have inadvertently uploaded not this zip, the one that contains their completed code, but the zip that they initially downloaded, also called p1 code.zip, and contains nothing that they implemented. This creates problems, and usually they have to submit late then. And generally submission problems like that of like, why, did this not work? It's like, oh, I uploaded the wrong zip. That's on you, and we'll lose you an engagement point for not checking. So hang around for a few minutes. It usually takes no more than 5 minutes, and check that the autogrid results actually match what you expect. This is much easier to do if you're not 5 minutes away from the deadline closing. So submit a few minutes earlier than that so you can see your results. That should be enough to get most of you started on this endeavor. We'll again have tutorial sessions in the evenings put on by staff members, and later on in the week I will attempt to release a debugging video that teaches some tactics and techniques which are useful in debugging the programs that you'll be writing, and generally useful. Particularly getting acquainted with the messages that Valgrind produces for memory errors of various kinds. This takes a little bit of practice, but once you get good at it, it will serve you for probably a lifetime of programming if you're in a Linux environment, and likely in other environments as well. Until I see you in lecture, I hope everyone has good fortune with this, and happy hacking.